So I will start. So Moinul, thank you for the recording. Okay. So thank you everyone for attending our talk today. And um, we are special interest group in for the technical IEEE Technical Committee on Cognitive Networks, and our group is mainly focused in the AI and machine learning in security. So we are mainly like right now we are 5 people in the group in the committee. We have our chair, Professor Suba. She's from Stevens Institute of Technology, and we are all other rest of the four are vice chairs. So me myself, I'm Devashri Roy. I'm an assistant professor at University of Texas Arlington. We have Professor Dolasa, she's from University at Albany, Sunny, and Professor Hanif Rabadi, he's from RIT, and Moinul Hussain, who is also here, he's from George Mason. So we are all excited to host you here. Um, okay, so just to give you a quick glance of what our group is, we have right now 468 members in LinkedIn, and we are constantly growing. There are various ways to join our community if you think this would be helpful for like your own research or you want to learn more about what our group is about. And you can also send us email um, like individually and learn more about us. So with that, I just briefly say that what type of activities we do as a group. So we have done earlier, previously mainly Professor Dola and Professor Suba, they had organized like distinguished faculty virtual seminar series over the last 2020 one and two. It started with Professor Vincent Poor, and then there are like many other distinguished researchers in the domain. And we have all the recordings updated, like uploaded in our website. So if you are interested, you can check out the recorded talks in SIG, our website, and also in the YouTube channel. So now, what we are doing now. So this is a very new initiative from our group, because it started with like all of like me and Moinu, like many of us are very new in this area, and we're assistant professors. So we just thought of what can we do, bring in more into the group on new activities. And we thought of why not to try like a Rising Star Symposium series where we'll give a platform for the speakers to represent their work in a job talk format while they are preparing to like preparing for academic or industry job, and like to engage with the community, and also maybe for the whoever is going to hire people, like sometimes can members from the faculty hiring committee also can attend these talks and maybe get to know what type of candidates are on the market. So this is our broader goal, and with that goal, we already have started in like in November, we had Professor Dr. Chiaie. She was from MIT and Brown University, and so she talked about absolute security in terahertz wireless links. So that was our previous talk, and today we are here for our second talk. This is our December talk, and mainly the logistic of the talk is that we are going to like request everyone would be muted in the entry, and we are going to stay muted. And if you have any question, please feel free to ask the question in the chat, and we'll talk like we'll ask this again at the end of the towards the end of the talk and by the moderator. But please feel free to type out your question in the middle. And so today our rising star is Dr. Nadia Yoza Mitsuishi. So she's from NIST. She's a postdoctoral researcher there, and she holds PhD and master's degree in telecommunication from University of Colorado Boulder, and her area of interest are spectrum sharing, radio propagation, and software-defined radios. So with that, I'll stop talking, and thank you, Nadia, for coming here and agreeing to our invitation. So now the floor is all yours.
Oh, thank you so much, Devashri, and thank you everyone for having me here today. I'm happy to be here and presenting a little bit of my research here at NIST. I will start sharing my screen. Yeah, so yes, so The title of this presentation is 5G and 4G coexistence measurements using software-defined radios. So this is a work that I've been conducting here at NIST, at the Shared Spectrum Metrology Group. That is part of the Communications Technology Laboratory, or CTL. So first, we'll start by introducing a little bit about software-defined radio. You guys might have already know about this. But yeah, like software-defined radio is a radio communication system that uses reconfigurable software-based components for processing and converting digital signals. And unlike traditional radio systems, these are highly flexible, versatile, and reconfigurable. So that's a really great advantage for prototyping and doing like these kind of measurements and new setups. So in other words, so in this way we have components that have been traditionally been implemented in analog hardware, for example, filters, amplifiers, modulators, demodulators, detector, etc., and are now implemented on software, on a PC, or an embedded system. So with these software-defined radios, we can implement systems that can be used for implementing and evaluating 4G, 5G, and other technologies. However, there's a lack of studies on intercell interference using software-defined radio measurements. So in other words, there's not much literature about like how these software-defined radio systems have been used for to study interference between different cells. And there's also a lack of reporting LTE SINR, so that's the signal to interference plus noise ratio to throughput mapping and multi-cell coexistence performance, considering hardware imperfections that we have in the SDRs and any type of hardware, and also noise figure, and also how to measure the noise figure using these devices, or for these devices, for these systems. So here we present the coexistence system roadmap for cellular and Wi-Fi. So first we have, for example, for cellular, it went from 4G LTE to 5G new radio, NR, and NRU that works in unlicensed bands. And from that, we'll have 5G licensed and unlicensed. And then on the other part, we have Wi-Fi that evolved from, lately from 802.11n AC to 11AX that works not just in 2.45, but also in 6 gigahertz band that has just been open a couple of years ago for unlicensed use. We also have 802.11AY that works in millimeter waves, and 802.11BE that will also work in the 6 gigahertz band. So for these two cellular and Wi-Fi systems, it's necessary to conduct coexistence measurements and optimization of the system so they can share the spectrum in a more efficient way. So the objective of this talk is to implement an SDR-based test setup to emulate and evaluate the performance of 3 wireless coexistence scenarios under very mutual intercell interference conditions. So in other words, we're implementing these 3 scenarios. One is 4G versus 4G, the other is 4G versus Wi-Fi, and the other is 4G versus 5G. So 4G and 5G work in frequency division multiplexing, or FDD. So that way the uplink and downlink are occurring in 2 different channels. And here we have the mutual intercell interference in the downlink channel, and they are occurring in adjacent cells. And Wi-Fi transmits and receives on the same channel. So the contributions of this work are the following. First, we are prototyping SDR-based intercell interference using programmable attenuators to control the communication link and the intercell interference link. We'll talk more about this later. So then we are also measuring the LTE downlink SINR, so signal to interference plus noise ratio to throughput. And we're doing this mapping, and we are comparing it with a theoretical upper bound and mapping reporting via SDR open source software. We are measuring the coexistence performance of licensed LTE link and a Wi-Fi link. for this case, we're not doing LTE non-licensed band, it's just a licensed LTE. So then we're comparing the system performance obtained with mutual 5G, 4G downlink interference versus just one-way 5G to 4G or 4G to 5G interference. And then we're measuring the impact of mutual 4G, 5G downlink interference for different levels of channel overlap, from adjacent to co-channel interference, and the region of channel overlap within each channel. And so for this talk, we'll first start by talking about the measurement setup, and we'll talk about the internal noise measurement of the system, then the SINR to throughput LTE mapping, then the coexistence LTE links, that's 4G versus 4G. Then we'll talk about 4G versus Wi-Fi, and then 4G versus 5G. So for the measurement setup, we have to first say that these are conducted measurements. For 4G and 5G, we're using commercial SDRs and open source software. So for 4G, we're using SRS Run, 5G Open Air Interface, and those are publicly available. We have installed those on computers that are running Linux. So for Wi-Fi, we're using commercial development boards, and for the software, they are based on OpenWRT, so we can configure the transmit power and set the channels as well for these tests. For the traffic generation, we're using iPerf, that is transmitting UDP traffic. And for the performance evaluation, we're considering the throughput and packet loss for the key performance indicators. So this picture corresponds to the SDR setup configuration of 2-cell mutual downlink intercell interference. I will talk about this setup in the next slide. So here we see the 5G versus 4G mutual intercell interference. So these are two adjacent 5G and 4G cells. And they're interfering with each other on the downlink channel. So for 5G, we have here the genome B that has one UE attached, and the same with the 4G. Genome B has just one 4G UE attached for the test setup that we're representing here. So in the right-hand side, we see that for this setup, we are using 2 Linux computers. Each of them has like 2 SDRs connected. So one of them is used for the 5G genome B, and the other for the 4G UE, and the other way around for the 4G genome B and the 5G UE. So for the 5G genome B, and then for the 4G genome B, we are using FITS 30 dB attenuators to protect the receiver port in the SDRs from overloading, because these are all conducted measurements. So then we're splitting the signal from the genome B into 2 using a splitter, and then we are using the programmable attenuator that has 4 channels. That way we can control precisely the downlink channel and the intercell interference. So the signal is simply split into 2. One will be the 5G downlink channel, and then the other will be the intercell interference 5G that will go to the 4G UE. So that way we're having each of the UEs that is impacted by the intercell interference from the other technology. 4G impacted by 5G and 5G impacted by 4G in a mutual way. So then for the internal noise measurement, we have to consider this noise floor equation in the SDR receiver. So we have the thermal noise of minus 174 dBm per megahertz. Then we have the noise figure that we are going to calculate here based on this setup. And then we are adding the 10 log 10 and then the bandwidth for this test. In this case, we're using a 20 megahertz bandwidth. So we have here we're doing SDR power measurements using a continuous wave or CW signal as a for transmission. So we're seeing that the system is linear. We are using attenuation, using a programmable attenuator from 50 to from 0 to 50 dBs. So we're attenuating the transmit CW signal. And that way we can find the conversion factor, because we want to map what is this conversion factor, because in the SDR, we have the data, the IQ data in the digital domain, and then we have to map that into the actual like RF domain. So we have to, and this has been measured using the power meter. So that way, using doing these measurements, we find that this conversion factor is around 100 dB. And here we're plotting the power spectral density of the internal noise floor, and then the noisy CW signal, and both have been measured and adjusted using this conversion factor. And then we're plotting here the ambient thermal noise floor, the theoretical one that corresponds to minus 174 dBm per megahertz. So doing this calculation, we find finally that the noise figure is around 13.1 dB. So we're using these measurements to find first what is the noise, the noise power in our measurements. So then we conduct this LTE or SINR or SNR to throughput mapping. So for that, we'll start by saying that we're using this SINR best case that was based on a table. So this is what we call the theoretical upper bound for this SINR, and then how this maps to the CQI, the channel quality indicator, and then the spectral efficiency. And then these other parameters are based on the 3GPP standard. And then they also put here the MCS, the modulation and coding scheme from 0 to 28, and then what's the associated payload throughput that should be expected based on the standard. And then we're also reporting here what is the SINR based on the of our measurements using the IQ data that we have recorded using the SDRs. But also these, in this case for 4G, the SRS run software is reporting the SINR and the throughput. So in this plot, we can also map what is the SDR, like the SNR and the throughput for each of these cases. For the theoretical upper bound, that is based on this first SNR, SINR versus CQI mapping, and then what's the SDR measure SNR and then the software reported SNR. So we see that both the measure and the software reported SNR are very similar, and then we compare that with the theoretical upper bound that is based on this table and the SINR to CQI mapping. So then we conduct the measurements of two LTE cells that are interfering with each other on the downlink channel. So for this setup, we're using LTE release 10 with features up to release 15. We're using FDD, as we mentioned before. So the downlink and uplink occur at different channels. So for downlink, we're centered at 2.68 gigahertz, and for the uplink at 2.58 gigahertz, and then the bandwidth of these LTE signals is 10 megahertz. So in these plots, we can see how the throughput and the packet loss get affected by different levels of SINR. And this again is the two-cell LTE downlink scenario. So we see here that we plot here again the theoretical upper bound that is shown in the red line. And then we also plot the SDR measure LTE downlink and reported LTE downlink for each of those two links that are interfering with each other in the downlink channel. So we see that the measure and the reported LTE to throughput are similar, which is expected. So that means that our measurements are very close to what this software, the SRS run software, is reporting. And we're comparing that with the theoretical upper bound. And yeah, both links are also, they are like the setup has been calibrated. So that's why we have that both throughput levels and packet percentage of packet loss are approximately similar for different levels of SINR. And of course, if we increase the SINR, we're expecting, and that's what we're seeing, having a better throughput as well. We're also conducting this coexisting LTE versus Wi-Fi links. So for LTE, we have FDD as well, and the downlink channel is centered at 5.22 gigahertz, and the uplink is at the same frequency as before, 2.56 gigahertz. The bandwidth is 10 megahertz for LTE, and then for Wi-Fi, it's based on AO2.11 AG, and the downlink and uplink are both at 5.22 gigahertz. And the bandwidth here is 20 megahertz. So we're plotting here the measured throughput versus SINR in coexisting LTE downlink and Wi-Fi downlink scenario. So in the red, like the blue line corresponds to the LTE that is impacted by Wi-Fi, and the black line corresponds to LTE that is impacted by Wi-Fi that has been impacted by LTE. So we see that the LTE throughput increases monotonically. That's the blue line. So here the LTE is not doing any listen before talk. It's just a licensed LTE. So the Wi-Fi throughput has significant fluctuations at SIR. So we're just using SIR, so signal to interference ratio. So for SIRs of 11 and 19 dB, we have these gaps in the throughput. And these are probably caused by channel sensing and transmission backoff, the transmission backoff algorithm that happens in Wi-Fi. And we don't see that in LTE. That's why LTE keeps increasing by having more like signal to interference ratio. Here we see the next scenario that corresponds to 4G versus 5G links. So here we're representing the distance profiles and the geographic layout. So we have two types of scenarios for this 4G versus 5G interference setup. So first we have the one-way 4G to 5G interference, or the other way around, only 5G to 4G interference. So that's only interference on either like one technology to the other, like to one technology to the other one. So we see, for example, here that each 5G and 4G cells have one UE attached. So the 5G UE has interference from the 4G. However, the 4G does not have interference from the 5G G0B, because that path is blocked by an obstacle in the middle, let's say a building. And then here we see, in the second scenario, we see the intercell interference. That means that you have mutual interference between 4G and 5G. So for the 5G, we have so 5G is interfered by 4G, and 4G is interfered by 5G as well. So, and then here we represent the link budget for example, the interference to 4G. So represent here the receive power level for 4G. So we have the transmit power for 4G that in this case is 46 dBm. The antenna gain, there is a sector antenna, so we have 16 dB of gain. Where for the path loss model, we're using the 3GPP model in non-line of sight conditions and urban macro cell. And we are considering losses through cables and connectors of about 2 dB, and we are just assuming that the receiver gain at the UE, 4G UE is around 0 dB. So that's for the first equation. And then for the second equation, we are calculating the interference from that 5G is causing to 4G as a victim. So we have the transmit power from 5G, the gain of the transmit antenna for 5G. So these values are basically the same for both 4G and 5G in these simulations to make this easier for our calculations, but also this is just an example. So then we have the same, we're using the same path loss model, same losses through cables and connectors, and then the gain for the 4G antenna. So then that way we can calculate the signal to interference ratio that corresponds to the interference from 5G to 4G. So yeah, we are subtracting this receive power level from 4G and the interferer power from 5G to 4G. So for the second case, we are plotting here 3 different locations of the UE in this configuration. So we're representing here the intended 4G to 4G link budget based on this distance, different distances here from 500 meters to 1.2 kilometers. And then the interferer 5G to 4G path for these other distances of like 2.1 kilometer, 1.9, and 1.6 kilometers. So that's what we're representing here for this 5G or 4G UE. So we have these 3 different UE locations, and then we have calculated using these link budget equations, and we're calculating the SIR based on these numbers, these equations. So we're representing this way different SIRs that we're going to use later in the. So this is a way of representing what we are actually simulating or emulating in the setup. So we have a high SIR of 25 dB, then of 15, medium SIR of 15 dB, and then a low SIR of only 5 dB. So then we represent the downlink frequency channel overlap. So 4G and 5G are getting overlapped at high and low portions of the downlink channel respectively on the left-hand side. And on the right-hand side, we are reversing the overlap regions. Instead of high and low for 4G and 5G, we're using low and high. So we're just swapping the 4G and 5G channel locations, and we are going to see if this has any effect on the performance of both 4G and 5G links. So now we are presenting the results of the coexisting 4G and 5G links. So we have one-way 4G to 4G or 5G downlink interference versus mutual 4G, 5G downlink interference. So the measurement setup is based on the following. First, for 4G, we're using band 1 FDD. So these are the uplink and downlink frequencies. And then for 5G, we're using band 66, that is FDD. And then both downlink bands, downlink channels, are overlapping. So we're just trying to represent a scenario that could actually happen in the real world. So we have 4G and 5G bandwidth, both of them of 20 megahertz. So we're implementing all of this in software-defined radio using, for 4G we're using SRS-RAN, and for 5G we're using OAI. So the maximum theoretical LTE throughput that we achieve with SRS-RAN is around 73.4 megabits per second at 28 MCS. This according to the 3GPP standard, but we are achieving here a little bit lower, just 73 megabits per second at the same MCS. So that way we're targeting a throughput of 72 megabits per second when we are simulating where we're pushing hyper traffic. And then for 5G, we have a little bit of a different story. So the maximum theoretical 5G throughput is around 81.9 megabits per second at 28 MCS. And at 25 MCS level is around 71 megabits per second. However, we're only achieving 58 megabits per second at this MCS of 25. So to keep the link stable for our measurements, we are targeting a throughput of around 55 megabits per second. So now we're representing the results of the one-way 4G to 5G or 5G to 4G interference. So here in the solid blue line, we see that this corresponds to the 4G with mutual interference. So, and then in the red solid line, we are representing the results with the 4G with only 5G interference. So that means that the 4G here is the victim. But there's no mutual interference here, but only interference from 5G to 4G. So we see here, we compare the solid blue and red lines, that the throughput is lower when we have one-way interference from 5G to 4G. So we have lower throughput and higher packet loss, as we see here as well. And that might be due to the fact that in the case of mutual interference, we also have interference, not just from 5G to 4G, but from 4G to 5G. So that might be, there might be an effect that the signal is like we have like lower throughput, I guess, because we have less interference anyway from 4G to 5G. So it's causing actually less interference if we have mutual interference. I don't know if that makes much sense, but that's what we are observing here. But yeah, that's the case of only one-way interference if we compare it with the mutual interference. So yeah, in other words, so if we have mutual interference, the performance of the other link of the interferer is also degrading. So that's why we can, that's one way of explaining why we have lower impact if we have mutual intercell interference. So then we are also comparing this case where we have varying percentage of channel overlap. So that means that we are, and that corresponds to this other scenario where we are overlapping the 4G and 5G channel. So here we're going from adjacent channel to co-channel interference. So from adjacent channel, we have to consider that we are only, so they are just like next to each other, 4G and 5G, but because they are just like low power and using SDRs, we are not using any power amplifier or any receiver filter. So we will see here then that we won't see any impact on an adjacent channel. So we are overlapping here in increasing 25% overlap, which corresponds to 5 megahertz, considering that we are having, like we're using 20 megahertz channel for both 4G and 5G. So here we are representing the results from adjacent channel to co-channel interference. So yeah, from adjacent channel, we see that there's a 0 reduction in throughput because we're comparing with the non-overlapping case. And we are plotting here for different signal to interference ratios. And then we have the highest or the worst performance, the highest reduction in throughput, or the highest also like percentage of packet loss if we have co-channel interference. So for the adjacent channel interference, which corresponds to the blue line that we mentioned before, this setup does not include the effect of power amplifiers that we have imperfect receiver filters that happen in the real world. So that's why we don't see any degradation in the throughput and packet loss. And then we observe that we have a higher overlap. We'll see higher performance degradation. And that performance degradation is not linear and is less increased as we go higher in the percentage of channel overlap. And then here we present the results of having different regions of channel overlap. So that corresponds to, again, these plots. So if 4G and 5G overlap in the high and low portions of the dynamic channel, versus low and high portions of the downlink channel, how this, like swapping the regions of overlap, will impact on the performance. So in these plots, we see that, so first we have to mention that the letter H corresponds to the higher region of channel overlap, and then the L represents the lower region of channel overlap. So for 4G, we observed that we have a better performance when the downlink channel is overlapped on the lower region. So we see that here, especially when we have 25% of channel overlap, that corresponds to the green lines. And it's not very pronounced when we have a higher overlap of around 75%. However, for 5G, the region overlap doesn't seem to have an impact, at least that is significantly enough to see that here clearly on the performance, because it's not consistent. For example, here for 25% channel overlap for 5G in the low and or high regions of the channel, we see that sure, like we can have a higher overlap when in the lower parts of the we see that we have a higher reduction in the throughput for lower portions of the 5G channel overlap, but then it's the opposite behavior for a little bit higher levels of SIR. And this correlates with what we see in the packet loss. So here is combined for both 4G and 5G. So these are just preliminary data shown. We have submitted these results to a conference, but these are all observations that are based on the SDR measurements, and we measure these like again, and it's consistent. So we still need to understand like why this is happening and do further measurements. So for the conclusions of future work, so first we have implemented that SDR configuration and measurement method for performance evaluation of 3 coexistent systems, 4G versus 4G, 4G versus Wi-Fi, and 4G versus 5G. We have measured the noise figure and provided a measured 4G LTE SINR to throughput mapping. We have observed that one-way 4G or 5G interference causes higher performance degradation than mutual 4G versus 5G intercell interference. Then we have seen that the impact of the percentage of downlink channel overlap between 4G and 5G in FDD mode is not linear. So the degradation increases at a slower rate for higher percentages of channel overlap. That's what we have seen before, that we have the degradation is lower for channel overlap of around 75% if we compare that with going from 0 overlap or adjacent channel to 25% of channel overlap. And then in 4G, the impact of the location of the overlap region in the frequency domain is not symmetric, and that's what we saw here in this plot. So for the future work, we want to implement new scenarios, for example, 5G versus 5G, and downlink intercell interference, then also do a similar setup for uplink intercell interference. Also want to do intercell interference in time division duplexing TDD mode. We also want to simulate coexistence with multiple cells, not just 2 cells as we did here. We want to conduct not just conducted, but also radiator tests, and we want to report as well the measurement and certainty by doing this more times. And we want to understand like why we're seeing this effect, and we'll try to mitigate the effects of mutual interference that we see here, for example, between 4G and 5G. So yes, that will be it, and thank you so much for your time today. Do you have any questions?
Thank you for the talk. I see there is one question from Rashedur Rahman. I was wondering whether the latency of the transmission was considered as a key performance indicator as part of the performance metric? And the second question is about, in the scenario of LTE/5G versus Wi-Fi coexistence, I was wondering whether plan for implementation of LBT in the future measurement. So the first question is about latency. So you showed throughput, whether latency is, or you also seen the latency.
Yes, that'll be, yeah, thank you for the questions. These are like great questions. So yeah, like we wanted to measure the latency as well, but at least for now, like we're just measuring this as that's what we can get easily with iPerf. But yeah, like we would like to get latency as well as a way of measuring how the performance can be degraded in these coexistent scenarios. Yeah. Yeah, we just need to figure out how to do this with iPerf. Because with Ping, we have the round trip time, and that's the, like two-way, like going back and forth, but we only want the one-way of like direction for measuring the latency. And then for the second question, yes, this is something that we want to do as well. Like we have a LTE LBT setup that has been developed here at NIST by one of by Dr. Yama. So he has implemented that on LabVIEW. So we would like to have that we would like to do similar measurements.
Okay.
Yes, that's also part of the future work. And we would like to also use the LBT functionality of that and then up converted to the 6 gigahertz band. So we also have Wi-Fi 6E boards, so we can do some kind of LBT functionality that will work with. Sure, it's just the LTE. We don't have the 5G NRU yet, but yeah, that's something that we want to do as well. So because before they've done these kind of measurements, but then like it was not with this kind of programmable attenuator, so that way it was not possible to control the mutual like downlink intercell interference and the downlink communication channel that precisely. But yeah, that's something we can do later. And then this other question.
So I think the same person has another question. The question is, I believe, is from the perspective of applications, like whether you have any plan to assess how different applications performs when we run them in coexistence scenarios.
Yeah, well, for now we're just trying to use this as a basic setup. So we have these other scenarios that we want to implement, but not in terms of the application system yet. Yeah, that'll be interesting to do for future work as well.
Okay.
But yeah, like we want to understand why this effects, right? Like for example, like one-way interference, or like how the location of the overlap channels, like and we want to mitigate these effects as well. But yeah, like that would be interesting to do for later.
Okay. So the next question is from Surya Saha. My question is regarding the implementational details. Can the system be implemented using Open 5GS as well, coupled with SRS RAN? Or is there any specific reason for choosing the configuration you chose?
Oh, yes. So we are implementing Open 5GS for the EPC for 4G. So yeah, that's what we're using, SRS RAN with 4G and Open 5GS for the EPC, for the core. Yeah, because that's they have a recommended setup. So we just follow the instructions there, and that's what we use for our 4G system.
Okay. I
For
don't see.
5G, for 5G, we're using OAI because that way we were able to, we tried as well with SRS RAM for 4G, but at least that's where I saw that when we're having different levels of SNR or SINR, the MCS was not adapting for SRS RAM. So yeah, like I asked in the forum, so it looks like it's not capable of doing that, which I'm surprised, but that's why I decided to use OAI instead. So that's why we are using OAI for 5G, not SRS RAM. And it's also based on the recommended setup that they put there.
Okay. So I actually have a question. So it's in your opinion, what coexistence problems do you think this test bed can help us solve?
Yeah, so we're very interested on this 4G versus 5G scenario that we were just talking before. We still want to understand like why these effects are happening, right? Like why we see that there's different, like that the degradation is not like that the impact of where the overlapping 4G and 5G channels is occurring, that's not symmetric. If it's like in the lower part of the 4G or the upper part of the 4G or the 4G channel. So for that, we want to do like further configurations, and we want to do simulations as well. And we want to confirm that with the setup. With 5G, we're not seeing that effect, but we still need to understand why. And yeah, we're also trying to mitigate the interference. So it might be interesting also to like do further measurements and like try to adjust some of the parameters. So yeah, because this is a problem that's happening in the real world. So that way we can just using these, like low-cost devices and flexible configuration to understand what is going on and how we can improve the performance.
Okay. I see that Professor Saha has raised her hand.
Yeah.
Yes.
So I have a quick question. Can you explain a bit more about the motivation of this work? Because somehow I feel like, and sorry that I don't keep track of all the things that are happening in 3GPP, but I somehow feel that they do have the propagation models, and based on that, the 4G and 5G are never deployed in the same region, right? Or same geographical location. But this study is actually showing that they are very closely placed in the way that one can interfere with another, right? And that's why I was wondering what's the purpose of this study, what it will lead to.
Mhm. Yes, they can be deployed at the same location. So, for example, the operators, the cellular operators already have the frequencies that they have purchased for specific regions, and that's why we are presenting these distance profiles and geographic layout to understand for two adjacent 4G and 5G cells of different vendors, for example. So, how this scenario can happen, right? Like at what distances the UEs for 5G and 4G might be located. So we will have these different SIR levels. Sure, like they should also implement DSS, dynamic share spectrum, so that way they can share the spectrum more efficiently. But that depends on the vendor as well. And it's, for example, it's a feature that it has to be purchased, and it's not, as far as I understand, like it's not like it's standardized, but then all the details are not there, or it depends on the vendor. So that's why we're just presenting these coexistence studies based on these SDRs, and yeah, for different SIRs. But in reality, yeah, this is a scenario that it can be representing, because yes, they are reusing the frequencies, and these are just like uncoordinated
The same vendor
different.
is deploying 5G and 4G the way that you have it over here?
That is my understanding.
I see. But why would they do that? It seems impractical.
Yes, yes, and that's why, for example, like
Because this will show up in the network planning, it seems. It's very obvious.
Mhm.
But still
Yes.
they do that?
Because they maybe for example from different operators they can do that. So I don't know. I actually don't know.
Oh,
right?
so
Like
you
if,
mean like different operators, not the same operator?
yes, yes. If they were the same operator, they will be able to coordinate, right? But then if they are not, there might be occasions where we'll have something like this going on.
But
So
then won't they
Mhm.
have different so don't they purchase the frequency bands in a location? So one, like Verizon will acquire a part of the frequency, right? So if your blue is Verizon and the red is AT&T, my understanding was that they will be purchasing two separate frequency bands and not the same ones. Is that not correct?
Yes, I don't know all the details of how they'll
Okay.
purchase the bands. Yes, it should be based on the region, but um yeah, like I guess in reality, sure, like they should be careful with this, but I don't know
Yeah, that's why
up to
I'm
what
wondering.
extent. Yes, up to what extent there will be, because we'll have problems of interference going on, right? Like I mean, not it's not the norm, like it's not common, but this might happen. But yeah, that's a great yeah, that's a great comment, and I'll look more into that because I'm also like interested of figuring out like how often this can happen and like to understand more the details of
Yeah.
the geography and the frequency allocations.
Sure. Thank you.
Thanks for the question. Mhm.
I think Devashi has a question. So since you're here, you can ask yourself.
Yeah, so my question was like more like towards your insight. So do you have any insight on like how much percentage of overlap maybe could be permissible, because you have tested different type of overlaps, right?
Mhm.
Suppose we are considering that there is an overlap like frequency domain, and I don't know, like X percentage, even if there is X percentage of overlap, still 5G and LTE could decode or partially decode the frames. Do you have any insight on that respect? Like, have you seen anything while you are experimenting?
No. Yeah, that's a great question. Like I actually don't know how much overlap we can actually see in the real world, right? Like how it depends on how these cells are deployed. But yeah, it will be great for us, like for example, to do measurements, to go in the field and actually see like what we can see deployed in 4G, 5G, if they are actually overlapping, and that way also understand like how we can see this problem happening in the real world.
Mm.
Probably might not be that much overlap, but yeah, that would be great to do. Yeah, I understand that. Yes, it's always great to like everything we do is backed by like actual measurements, field measurements.
Yeah. Okay, great. Thank you, Nadia.
Thanks, Sebastian.
Yeah, so it's when I was looking that overlapping thing, I was thinking from a spectrum utilization perspective, because we sell the spectrum in different chunks, whether there is a way to pack them. And let's say just say 20% of overlapping is okay. 4G, 5G can still coexist. So it will save us some spectrum, especially in the mid band.
Okay, so how much? 20% is okay? Or...
No, I'm just asking. When I was seeing that, I was wondering that
Yeah,
like it
that
would
would
be
be great.
something interesting to see.
Yeah,
Mhm.
like in the CBRS band, the PAL users, they're not with the radar, but the PAL users like 5G, LTE who are coming, who can coexist at the same time. So if there is some permissible overlaps, that would be great. Yeah. So this kind of measurement study, if they can be used for such like inferring that, that would be great.
Also, I was not sure about the current status of LTE unlicensed way, and if some of those can be utilized for coexistence purposes. Not, I mean, LTE-U was mostly targeted for coexistence with Wi-Fi, but something for 5G, 4G it can be done similarly, I guess.
Mhm.
Yeah. Yeah. Yes, I guess so. Yeah, it'd be great if we can do, yeah, like more measurements and do, like we don't have any like 5G NRU setup, but maybe we can do some simulations. Like to coexist, for example, with Wi-Fi, or for example, like to implement some kind of DSS, so we can have spectrum sharing between 4G and 5G.
Okay, so I have one last question. It's based on your experience, what do you recommend protocol-wise for better coexistence?
Yeah, for example, if we see here, right, like based on these results, but might be due to the specific configuration in these SDR devices, so we need to do further like simulations and measurements. Yeah, here we see that there's better performance when the 4G, for example, is overlapping the lower region. So instead of, yeah, so that also indicates like where 4G and 5G should be located, if they should be using the lower part of the channel or the of the band, or like the upper part of the band. So these like some measurements like this can be helpful to understand what can be more like optimal when we are deploying 4G and 5G systems right now. But we need to do more simulations and more measurements, and then like understand like why this is happening and propose mitigation techniques. But yeah, for example, this, right, like where 4G and 5G can be located when they will have, for example, adjacent channels. Yes, as you all mentioned before, yes, it will be nice to understand like what's a maximum percentage of overlap, and based on that also do a more like, a better like frequency planning for 4G and 5G, for 5G deployments. Yeah, but yeah, that's what we can say for now based on these measurements.
Okay. All right. Thank you. It has been very interesting. I hope you can see it in our questions. We're very interested in seeing all these measurements that you have done.
Thank you so much. Yeah, thank you everyone. I really enjoy like hearing about your comments, questions and concerns. I look more into all these topics.
Okay, all right. So if none of us have any more questions, then this is it for today. Thank you again, Dr. Nadia. Hope we will see you again sometime.
Thank you so much, everyone, for your time.
Thank you.
Yeah.
Thank you.